Density is a reoccurring theme in many of the topics that we discuss. So in this video, we'll look at what density is and how it impacts the different areas in earth science. What is density? Well, density is the comparison between an object's mass and its volume. Mass is the amount of matter in an object, while volume is the amount of space that it takes up. So when looking at density, we're comparing the two to one another. How much mass is in a certain volume. Density is also thought of as a measurement of the compactness of matter. Basically, the closer the molecules are to each other, the higher the density, where the further apart they are, the lower the density. So in these two examples, I only have a few molecules here, but a lot of room. So the volume for those molecules or atoms is high, whereas the volume in here, it's a little more cramped because there's a lot more stuffed in. So the compactness in this example, or this substance, is much higher than in this one. So we would say this has the higher density compared to that. To give you another example, compare these three objects. At first glance, you can clearly see they're different sizes, but when I look at them, if I were to say that one red dot equals one atom, okay? Now we can't see atoms, but let's just pretend we could. If I did my math correctly, there are 16 atoms in this block, in block A, and there are 16 atoms in this one, and there are 16 atoms in this one as well. And that's significant because if I were to count every one atom as a gram, which it's not, but let's pretend it is, then I could say that each block actually has a mass equal to 16 grams. I know that they're not the same size, but the amount of matter in them is the same, so their mass is going to be the same. But what happens to their volume as I go from A to C? Well, the volume here is very low, not a lot of space, so I have a low volume. Whereas over here, I have a much higher volume. And as I change my volume across, what my density is impacted because I'm changing my denominator. If you're familiar with the math here, and I'll show you the formula, density over mass over volume, I'm keeping my mass the same, but I'm making my volume much, much bigger. And what's that going to do? It's going to shrink my density. So without getting any more detailed with the math, it's basically comparing the two, mass and volume, to one another. So here's the formula. The formula is always going to be given to you on your earth science reference table. No need to memorize it. And when we look at the formula a little more closely, we're looking at it like this, that the D, the abbreviation, is density with the units grams per centimeter cubed. And that's equal to the mass, or the amount of matter in an object, measured in grams, divided by the volume, the three-dimensional space an object takes up. That's usually measured in centimeters cubed. Of course, it can be measured in milliliters. Those are interchangeable. Now, one thing that I love to show with a three-variable formula like this is something called a density triangle. The way the density triangle works is you can put density here, right? That's D, M up here, and V down here. And what that gives you is the ability to always calculate the missing variable. So in this case, let's say I didn't know my density. If I covered up my density, it would be mass divided by volume. See how mass is on top, volume's on bottom. But if I didn't know my mass and I covered that up, it would be density times volume. If I didn't know my volume, it would be mass over density. So with this simple triangle, I can figure out whatever's missing in my three-variable equation, which we will have to do. Moving right along, let's take a look at how we can apply that formula. So here's a gold bar. What is the density of this gold block with a mass of 193.1 grams and a volume of 10 centimeters cubed? So using our formula, D equals M divided by V, I substitute my values. So now I'm looking for the density. I know that mass, as it states here, is equal to 193.1 grams, and the volume is equal to 10 centimeters. So I'm going to plug this into the calculator exactly as I read it. I'm going to punch in this number first, then my divided by, and then this number. And if I do that, the number I get is equal to 19.31 grams per centimeter cubed. So that is the density of gold. You can look that up if you want. It should be the density of gold. Now, in this example, I have a gold coin. Clearly, a gold coin is not the same size as a gold bar. They're different. However, it's going to reveal a very interesting and important property about density. Using the same formula, density equals mass over volume. Once again, I substitute my values. Here's my grams, my mass, here's my volume, and I divide in my calculator by putting this number in first, divided by this number. What do I get? 19.33 grams per centimeter cubed. Now, why is that significant? Because both my coin and my gold bar are made of pure gold. And if something's made of a pure substance, no matter what its size or shape is, its density should be the same. So here I have a gold watch. And let's pretend the gold watch has nothing else in it. It's all gold, solid gold. What's its density going to be? 19.3 grams per centimeter cubed. Why? Because the gold, the ratio of atoms, its mass to its volume, is never going to change as long as it remains pure. So there are a couple of things that can impact density, and we'll be talking about that in the next couple of parts of this video, but I want to point out that basically what I'm saying about gold in any example that I do think of at different times always comes back to that the density of material is always the same, no matter what, unless the temperature and the pressure are changed. So if you keep pressure and temperature the same, if you have a substance, its density is going to be the same no matter what. To give you another example, let's say I have a wood block like this, right? It's made of a certain type of wood, and that wood has a density of 0.65 grams per centimeter cubed. I cut that piece of wood in half. Now I have two sides. Both sides are going to have the same density. All right, most people would think that it would be halved, but it's not. It's because when I really look at the molecules that make up that wood, even though I cut it in half, the ratio of atoms hasn't changed. So the mass to volume ratio is the same, and that's why the density doesn't change. It's a hard concept to master, but if I wanted to change the density, I'd have to burn it or heat it up, because by doing that, I change the arrangement of the atoms. And when that happens, I wind up with a different density. So let's look at the times that density does change. So density can change if I change my temperature. So in this situation, I'm starting out with a cool temperature. When the atoms or the molecules are cool, they're not going to move very far. But if I increase the temperature, well, I'm going to increase their speed. They move a lot faster. And if they move faster, their density is now decreasing because they're separating. So basically, increasing the temperature will decrease the density. The best example that I can give you is a hot air balloon. The way that a hot air balloon works is it's filled with a gas like helium, but there's you can't really see it well, but here there's a little flame, and as that flame heats up the air in the balloon, that air starts to expand. And expanding means it becomes less dense, and it starts to push on the outer parts of the balloon because it's trying to escape. It's being heated up and it's separating, and that changes the density inside the balloon, making the density in the balloon low compared to the density of the air outside. And that's what makes the balloon rise. If we want to make the balloon descend or come back down to Earth, well, then we turn off this flame and all this air comes back together, and that changes its density again. Another way you can change density is by changing the pressure. Less pressure, all right, so this is a canister with a stopper on it. less pressure allows the molecules to move around freely and not bump into each other. This will decrease the density. If I increase pressure, if I actually squeeze down on the molecules, now I'm forcing them to bump into each other. I made it a lot more compact. And that's what density is a measurement of compactness. So that's going to increase density. So basically, as pressure increases, density will also increase. A good example of how this works is in our own in the layers of the Earth. So if you look at how the Earth is layered in our reference table, you can see here that as we go deeper, and I'm looking at these numbers, I'm getting to higher and higher densities because all the rock that makes up this part of the Earth, these layers, is pushing down on the inside of the Earth. That's increasing the pressure. So I'm getting to denser and denser layers as I go towards the center of the Earth. And one more example, phase changes. That's going from a solid to a liquid to a gas, changing phase. By doing that, we change density. So going from a solid to a liquid, look what happens to the molecules. The molecules are all nicely arranged here. Now they're a lot looser. And that changes the density by decreasing the density. And if it goes from a liquid to a gas, now look at all the space between the molecules in the gas, a much lower density. So going from solid to liquid to gas decreases the density. A significant property within density is buoyancy, and buoyancy is the ability to sink or float. So how something will sink or float is very dependent on its density. We usually measure buoyancy compared to water, and water has a density equal to 1.0 grams per centimeter cubed. That's liquid water. If I freeze it, that changes its density. So basically what happens is you can look at how dropping an object in water, if it sinks, well, that means that its density has to be greater than 1.0 because it's sinking in the water. If you drop an object in the water and it floats, then we know that its density is greater than 1.0. So knowing something about the buoyancy helps determine its density, but whether or not it's going to sink or float. As a whole, and what I mentioned in the beginning of the video, the Earth is running on a couple of different themes, and one of them is density, because density really drives a lot of the relationships within the major areas of Earth. So for instance, we think about the ice that covers the Earth. There's 10% of the Earth's surface covered in ice, and that ice can float in water. So that's a relationship that's very important, how that ice floats and interacts with the water, and also can move and float. Weather events, for the most part, involve the differences in density between hot air and cool air. That interaction between hot air and cool air is what creates things like hurricanes and tornadoes and rain and snow. The molten rock that's trapped under Earth is called magma, and that magma is channeling in these big currents based on the density that's changing because of the pressure and because of the heat that it's exposed to. And because of that, that's where theories like continental drift and plate tectonics all come from, the changes in density in the layers of the Earth that are liquid. And even looking at those layers of the Earth is a layered object. It has different layers based on its density. The deeper you go, the more dense the material is. And that's really how the Earth formed. The more dense material went towards the center, and all the less dense material, the dense material went towards the center, and the less dense material made up the crust, the outer part. In our ocean current systems, warm water floats on top of cooler water. This creates a kind of a global circulation pump that takes really, really cold, salty water from the North and South poles and moves it and distributes that cold water and that salty water throughout the entire Earth, whereas heat from the equator gets pushed to the south and north poles. And this creates this global current. And because of that, it controls a lot of the weather events that take place on Earth. So all based on density. And in the universe, in our own solar system, there are 4 terrestrial planets. Earth is one of them. They're all rocky, dense planets, whereas the 4 gas giants, which includes Jupiter and Saturn and the rest, they're all low density. So in our solar system, the density of the material that makes up the different planets really will determine the category that it falls into. So density is a very important measurement and something that we will talk about a lot in earth science. So that's it for now. Thanks for watching.